whole file, we strip off the lines text, and then we say if line.find from is greater than or equal to 0, then we print it. It gives you -1 if it's not found, and so reads all the lines, and once in a while it'll print it out, reads all the lines once in a while, print it out. So that's kind of like a needle in a haystack. To use regular expressions to do that, we have to import the regular expression library. These lines are the same. We're going to loop through, we're going to strip. And now we're going to say if re.search. The way to say this is within the library regular expressions, go find the search function and search for the string from in the string line. Okay, so this is the line to search, whereas here it was more object oriented where we say line.find. Here we say re.search and we pass in line as parameter. These two things are equivalent, which means most of the time it's going to run, and once in a while it'll hit a line and it'll print that out, and then it'll finish the whole thing. So that is taking and doing what we would do with the find operation with regular expressions. Now, searching with regular expressions has these special characters, and so here we have the same basic code, except now we're saying if line starts with from. So we're not using find anymore, and that way we're only going to get that thing in the first position, not like blah 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 from colon. We don't want that to match. We only want it to match here at the beginning of the line. And so that's what we use line starts with. So it's going to do the same thing and find lines that have the prefix and print those out and then be done. Now in regular expression search, we don't, in a sense, change the method. We have a certain number of things we can do with strings based on what they've built in. But in regular expression, we actually can turn this first parameter into code. And so what's happening here is the caret, if you go back to the little cheat sheet, caret means this is the beginning of line. It's a virtual character that matches the beginning line. It's like from that starts at the beginning. So from at the beginning does match, and from in the middle does not match by putting that little caret there. Same thing, line is what we're searching, and then from is what we're, caret from, line at the, from at the beginning is what we're looking for. And so again, it does the exact same thing. It only prints lines that have from colon as the first character in the line. So the difference is we look for a method, and the other one is we program the regular expression. So we're going to run out of methods in the string class long before we run out of things that we can do with regular expressions. And so a couple other special characters, that caret matches the beginning of the line, so caret matches the beginning of the line. This capital X matches itself. Dot is a wildcard that matches any character, and then some of the characters in regular expressions modify the immediately preceding character. And so that says look for a line that starts with X and then has many characters, that's what these two things, 0 or more characters followed by a colon. And so you can see that it's this sort of like expanding stamp. It's like, oh, there's an X at the beginning of the line, that line, it looks good. I got some characters here and then I got a colon, that's good. So this is an X, some characters, and a colon, check. X, some characters, and a colon, check. X, and these things, you know, away we go. And so you can, that's what's going to match. And so you can see how some of these characters are special. Again, go back to your cheat sheet. Some of them are special and some of them are actual characters. And this colon and X are just, they're not special, they're just the characters. Okay? Now, sometimes you want to be a little more clear on your match. So let's take a look at these lines that match that particular thing that we just did. So we have these two, x-civ colon, x-d stam dash result, like these are from mail messages. And then one of the mail messages has a line in it that says x-plain is behind schedule. And this matches. Is that what you really wanted? And so what we can basically say is, because this is an x, this is some number of characters, and that's a colon, it matches. It has to match. That's this rule applied to this line results in a yes. It does. And so how can you be a little more clear as to what you want to match and what you don't want to match? So we can write code. So now what we're going to say is we want to match the beginning of the line, and we want to capital X, and we want a dash. So now we're going to match those first two characters, X dash, at the beginning of the line. Caret X dash says first two characters of the line must be X dash. Now we have another special character. Again, refer to your cheat sheet. Backslash capital S means a non-white space character, right? Any character other than white space. And then plus means one or more times, one or more non-white space characters. That's what this whole thing says. One or more non-white space characters, and followed by a colon, which is just a character. So now we have X dash followed by one or more non-white space characters followed by a colon. X dash followed by one or more non-white space characters followed by a colon. Here we have x dash followed by one or more. Whoops, there's a space there. And so this doesn't match. Even though there's a colon there, it means that between the dash and the colon, you can only have some number of non-white space characters. So this is a no, it does not match. And so you just can, if you didn't want to match this, you then sort of create a more precise, we could even have a thing that said, I want x dash with an uppercase character, uppercase letter, if you wanted to. And so there's all kind of fine-tuning if you sort of learn the structure that you've got to do. And so that's kind of the matching, where you're taking a whole line and taking this template and deciding if the template anywhere in that line matches. And now what we're going to do is use this to actually pull data out of strings using the regular expression library. So now we're going to move from merely matching to matching and extracting. So we're going to say, hey, I would like to not only have you take this template, this little pattern, the string pattern, regular expression pattern, run it across the line. I want you to give me all the ones that match, and I want a list of those. And that's what we're going to use the find all. So search gives a true false. Find all gives a list of all the strings that match. So if there's 4 of them, you'll get 4 things in the list. If there's nothing that matches, you'll get an empty list. So let's take a look at what we got going here. So instead of calling search, we call find all. We still pass in the string that we're looking through, and then we have our little template pattern. And this is a new bit of regular expression. Any little bracket operation, square bracket, is one character. That's just a character, but then there in between here is a set of allowed characters. So 0-9 means a single digit, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. But that's really one character. And then we have, so that's one character. And then when the plus applies to that, which means if we look at this whole thing says 1 or more digits. That's the code we write in a regular expression that says 1 or more digits. And we're just going to use that in our regular expression by itself. So we're going to look for any string that's 1 or more digits and pull it out and give it back to me. So it's going to look. So that's my little template. Stamp, 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 stamp. Oh, got it. Stamp, 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 stamp. Oh, got it. Stamp, 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 stamp. Got it. So what we get back after we ask find all to find all of the 1 or more digit strings is 2, 9, and 42. So it actually parsed it, it split it, it found all these things and said, I found them all for you, and here they are, 2, 19, and 42. So it's a list of 3 strings, because that's how many it found. Now it might have found none, and we would have got an empty list at that point, but it found some. Okay, so just as an example, we did this thing, we get 2, 19, and 42, but if I said this, that basically is an uppercase vowel, A, E, I, O, or U, so that's one letter, and that's 1 or more. So it's saying, something like A would match, E, I would match, O would match. But if you look now, it's saying, okay, I'm looking for 1 or more, minimum 1 or more uppercase. A, E, I, O, U is a set of characters, 1 or more uppercase letters. And so it's like, look, do you find, oh, there's an uppercase, but it's an M. No, 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 no uppercase, no uppercase, no uppercase, no uppercase. Found nothing, did not find anything. And so it gives us back an empty list. And so it's like, find all the things that match this, and the answer is none matched. Here's your list of nothing. Okay, and so you have to check. That's how you have to check even if you got something, because it's not going to return you false. It returns you a list with no items in it. Now, the way it works, like I said, it sort of is taking this template and stamping it across the line, stamping across the characters. Now, there's a behavior that might not be intuitive you at the very beginning, but the notion of what we call greedy matching, and that is when it can match more than one possible string, overlapping string, it chooses the largest overlap of the overlapping strings. And so the easiest way is to show this with an example, and we're saying I want something that starts with an F with 1 or more characters and ends with a colon. So that's my little stamp, that's my template. So starts with an F, good, that's good. 1 or more characters, da 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 da, have a colon. So that could be from colon. That would match. But look, I've got another colon here, and this is just continuing on with 1 or more characters and this. So the question is, do we get this or do we get this part, right? And the answer is, with greedy matching, is we get the larger of the two. Okay, and so what you get back is somewhat counterintuitive. You get the whole thing as the match, from colon using the. We could have got from colon, but the reason it picks this is this one's longer. So anytime it has a choice, it picks the longer one, and that's what greedy is, meaning it'd probably be better described as larger or tending toward the longest string or something like that. So you can, of course, suppress this behavior. Like everything in programming regular expressions, you simply add another character. And so now it's going to say, I would like to start with letter F, any character, one or more times, and then this question mark, this is still one, one little thing, non-greedy. Okay? And so that just says do it not greedy, which just means that it prefers the shorter of the strings. And so now it could still match this string or this string, but because it's been told to not be greedy, it chooses this string instead, and that's the string that we get. And so that's the not greedy, and you just add the question mark after the asterisk. So it's usually an asterisk question mark or a plus question mark, though that's a two thing. That's 0 or more characters non-greedy, and that's 1 or more characters non-greedy. Actually, most of the time, it seems to me that the non-greedy would be the more reasonable default, but that's not how it is. Greedy is the default and non-greedy is optional. Now, we can play some more with this stuff, okay? And so let's take a look at this little example where we have a non-blank characters, \S, 1 or more of those non-blank characters, followed by an @ sign, and then again 1 or more non-blank characters. So this is looking for strings that have an @ sign with non-blank characters on both sides. This is an example of where it sort of comes to this @ and it goes this way, and it does it in a greedy manner. If you told it to not be greedy, it would give you these 3 characters. But we're telling it to go greedy, so it goes all the way to here and stops at this blank, and then stops at this blank. And so that's a nice little thing. Find the @ signs, go to the first blank, and pull that stuff out. And so that, with one little match, you've pulled this thing out. Now, of course, we've done that before with other techniques. So that's just another way to pull stuff out. Now, if we get this whole thing, but what if that's not exactly what we wanted? We can tell, we can give it a matching string that's different than the extracting string by adding parentheses. And so here's another example where we basically say, this is our string. We want to match from at the beginning, followed by a space, followed by, ignore the parentheses for the minute, 1 or more non-blank characters, followed by an @ sign, followed by 1 or more non-blank characters. So this is also going to, if there's no from, it's not going to be looking for that, right? So it demands the from is here, so it matches that, and the space is demanded as well. And then it says, oh, non-blank characters, great. I got an @ sign, great. Non-blank characters, oops, stop there. And so this is what's going to match. Now the key is that we don't actually want that back in our extraction. What we really want back in our extraction is this part right here. So what we do is we put parentheses in. Parentheses are code. They're code in the regular expression world. Parentheses say start your extraction and end your extraction. And so when you do this with a parenthesis, when you do it, without a parenthesis, you get the whole from, right? Without a parenthesis. Oh wait, no, okay, that doesn't have the from in it. So, but if you do that with the parenthesis, you match the from, but you only get this bit to come out as well. So you can add this to make the matching part more precise, but without changing what you get returned, and you specify what you want to get returned with the parentheses. So next I want to show you just a couple of different ways to use these newfound skills. So now what we want to do is use some of these newfound skills in some more practical applications of regular expressions. So let's go back to the way we first tore apart strings and look at the situation where if you recall, we just wanted the host name, right? This is an email address and we're interested in the host name. So we have this string and we go find the @ right? The find looks up and tells us the @ is at position 21. And then what we do is we say, okay, let's look beyond there to the space, and that tells us the space is in position 31. And then we're saying we can extract starting at beyond the @ sign up to but not including the space by saying @pose +1 colon space position. And when we get that, now we have to have a thing that decides to only look at this on from lines, but then it can print out the host that is extracting of this information. So that was one way that we did that, right? One way we did it. The next way we did this was the double split pattern, right? So we said, okay, let's take this line, let's break it into words based on spaces. That's what words is. So that's 0, 1, 2, 3, 4, 5, 6. And then we know that the email address on lines that start with from, space, is the second one. So we pull out email address, which pulls this bit out into email. And then we're going to split that again based on the @ sign. So we're going to split this part again based on the @ sign. So it splits right there, and then this becomes the 0 and 1 in pieces. And then pieces sub 1 is that host. And if we print that out, we get the host. So that's the double split pattern. Nice thing about that is you don't have to keep track. The little +1 is kind of annoying to use the space position. That previous one, that's just hard to remember. It's just, I've written this code way too many times in my career, and I've made mistakes, and I have to debug it every single time, and I print all these numbers out. I'm like, did I get it right? Oh, I did it in Python, I did it in Java, I did it in C. Wait a sec, I did it differently. And so this is a lot cleaner. I mean, I can write this every time, and I know it's going to work every time. I barely even need to test this code because it's so obvious. So double split is another way of extracting stuff. But if we look at this thing with the regular expression, we can say, oh, okay, let's use a regular expression to do this. So we'll start looking through the string. We'll start by saying, hey, let's look until we find an @ sign. Then let's start extracting with the parentheses. And then once we have found the @ sign, let's look for non-blank characters. This is a set of characters. This caret as the first one means not a blank. So that's another way to do non-blank. Not a set of characters which are everything but blank. That's what this little bit is saying. Star means 0 more times, which means it's going to run until it finds a blank, which is going to stop it. The greediness is what keeps pushing it, right? This is a greedy match. That asterisk is greedy because there's no question mark after it. And so that does go and starts at the @ sign with the parenthesis, goes to the space, and that's the end parenthesis, and that's what prints out. Now, Y is going to be a list. That's a one-item list that has the string in it that we're looking for, but you can just go sub-0 to get that guy right out of there. Okay, so that's sort of the regular expression version of it, but we can make this a more fine-tuned thing. So we can say, look, we also want to pick the line, and we want to know if we don't get that line, we want to skip it. If we do get the line, we want to extract the data, and we can do this all in a single regular expression. So again, we say start from the beginning of the line, and it's got to be a from, followed by a space, and then followed by any number of characters, dot star, followed by an @ sign. So this has to match. We see a space, then we're going to have any number of characters, and then we're going to see an @ sign, and then we're going to start extracting, and then we're going to go non-blank, 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 up, blank, and extracting, and out that comes. And this has the advantage of the previous one in that makes it much more precise. If we look at the previous one, while it works on good lines, it might actually trigger on lines that we actually don't want to see. So this allows us to refine it so it only actually does this to lines that we care about. So it's sort of both an if statement and a splitting, extracting going on all at the same time by having a bigger string that we're matching than we're extracting. It's a way to kind of clean up your data. So here is a simple program that we're going to just put all this together and actually accomplish something. And so we're going to read through and look for lines in a file that have this form. And we're going to extract this number, and then we're going to compute the maximum of this. Okay, so we're going to extract this number and then convert it to a float and compute the maximum. So, we're going to open a file, we're going to write a for loop, we're going to strip. So we're going to do this for every line of the file, but the first thing we want to do is not get line. We want to discard all the lines except ones that have this. So our regular expression is look for lines that start with x-d spam-confidence : So that's a pretty strong match. If that's not there, we're not going to get anything. And then there's a space, and then start extracting, and then go as long, one or more digits and dots, that's a single character, and that's one or more, and then stop extracting. So that says start extracting, greedy, stop extracting. And so that's what we're going to get. Now, if the line doesn't have this, it means missing in some way, whether it's this prefix or this number. If the number's missing, it's going to fail too. We're going to get back a list, an empty list. So the first thing you have to do is check to see if you actually got a match. So you say if the number of items in the list, len of stuff, is not equal to 1, continue. And so this is the skip all the lines that don't match. Skip. So there could be thousands of lines that don't match. But then when this match hits, it's going to come down and fall through, right? So that most of the lines will skip up, but then when we actually get one, and we know instantly that we've got one, and stuff sub 0, because that's what we extracted, is this number. And we can take the floating point of it, and we append it to our list. We made a list to store them. That runs. The list grows. And then we just say, what was the largest one? And so you can run this and see that. We have an escape character, and the whole idea is sometimes all these little special characters that make a lot of sense to us, we actually want to search for it. So what if we want to search for a $? Well, we just prefix it with the backslash. And that just means this is a real $. So $$ is a real $. So this says, I would like a $, followed by one or more digits or dots. And so that's going to match a $, followed by one or more digits. Dots are okay. This is a set, remember. 0-9 or dot, that's a set of the list of legit characters. This is a range of characters that's a shortcut to how to make the set. You could make it be 0, 1, 2, 3, 4, 5, 7, 8, 9 dot, or 0-9, and it assumes that. And that's one or more. So then it stops because this is a space. It's greedy matching. Then it pulls this out. So that's kind of why greedy has to be the default, because otherwise, if it wasn't doing greedy matching, oops, come back. If it wasn't doing greedy matching, it would, if it wasn't doing greedy matching, it would stop here, because it would find a $. Non-greedy would find a $, and one character, and then it would give us $1 rather than $10. So, in summary, regular expressions are a cryptic but powerful language, and they're an acquired taste. I bet eventually you'll find them fun, even though on your first impression you might not think that they're so fun. Welcome to Networked Programs. This is Chapter 12. Now we're going to learn a little bit about how we talk to resources on the network using Python. Now, this is a really quick introduction to how the network really works. I have a whole book that I wrote. It's also translated into Spanish on how the network works, starting at the very lowest layer, packets and everything, right on up. And it's actually really easy to read. I wrote it for a high school audience. It's a short book and pretty easy to read. So if you read that book, you will understand that there is this layered architecture, the TCP architecture that sort of runs our network. At the lowest layer, that on one side here, this is your computer and this is a server computer. And if you sort of want a web page, it goes across the network, does this like 15 or 20 times, then it goes up into the server, reads the data, and then the data comes back, 15, 20 hops for the packets, and then it's shown to you as what you see. And so that's how it works, and there's these layers that we're not going to talk about in this section, but I talk about in that book. The layers of the link layer, which talk about how to get over one hop, the internet layer, which talks about how to construct, say, 15 or so hops to get packets back and forth. That's the sort of lower level bits. We're going to start at what we call the transport layer, and that's the layer where your computer sort of assumes that it can make a phone call to another computer, another process running on a program on this computer, talks to a program on this computer, and then it kind of comes back. Okay, and so we're gonna leave this alone. We're going to ignore it. We're going to assume that there's this nice reliable pipe that's going from point A to point B, and what are we going to do with the pipe? But if you're interested, take a look at the book. So we're going to start with a pipe, some kind of a connection. We have two processes. process, process, and we have some kind of a connection between them. And it is a connection that we can both use to talk and to listen. In nerd terms, we call these things sockets, and that is one process running on one computer, another process running on one computer, another second computer connected through the internet somehow, and one computer speaks into that socket and it comes out, and the other computer returns something and it comes. And so this is a bidirectional protocol of data, which is a series of, in effect, data phone calls between applications. So the application might be on your side, this might be your browser. Chrome, Firefox, Internet Explorer. On the other side, this is a web server. Might be Internet IIS, Internet something something from Microsoft, or Apache, or Java Tomcat. There's another program, and you are making phone calls between these programs. Now, in general, these servers here stay up all the time, and you sort of just can make a request when you feel like it on in your program. But that's what we're going to do, and this is what we call a socket. So that little connection, that phone call, that data phone call, is what we call a socket. Now, you have to decide which of the systems you're going to talk to, and then which of the services on those systems, or which process. And so we have this concept called port numbers, and they're best thought of like extensions on phones. So one organization has one phone number, and it says, please enter the extension of the party you'd like to talk to. Well, that's kind of what ports are. They're like, here is, I'm a server and I'm connected to the internet. Please enter the extension of the process that you would like to talk to. And so, for example, there might be processes running on various computers, and so the email is known to hang out on port 25 or extension 25. Login, insecure login lives on port 23. Insecure web lives on 80, and secure web lives on 443, and there's a couple of different protocols. Say if you have your mail stored on Gmail and you have a local mail client, say like Thunderbird or Apple Mail, that talks a protocol to pull that mail across, and those live on various ports. So these ports are those extensions, and by convention we have standards that tell us what to roughly expect at those ports. So when you're talking to port 80, you expect to talk to a web server or an HTTP server. If you're talking on port 23, you expect to talk to a telnet server, and on and on and on and on. And so these are the extensions, the typical, commonly used default extensions for various network application processes that are serving us data. Now, sometimes you'll go to a URL and you'll see in that URL there's a colon and a number. That means it's a web server that's running on a port other than the official 80 or 443 port. Now, in Python, we can talk to these sockets, right? We can just talk to them, and it's really easy, surprisingly easy. We have to import socket because that's a library. It comes with Python, but until you can use it, you can't use it in your program until you say it. And then you basically in the socket library you call socket function. That's what that syntax is saying. You're making a socket. Now the key to a socket, it's sort of like an unopened file handle. It's half of a file handle. It's an outward looking thing that's not yet connected. These parameters, you're just going to type them in. This says we're going to make a socket that goes across the internet, and it's a stream socket, which means that it's a series of characters that come one after another rather than a series of blocks of text. There's another kind that's harder to deal with, but we're going to do this. So this, don't worry about this line. Just know that this creates a socket but does not associate it. The very next line, we get back a socket object in this variable that I'm storing in the variable mysock. And then when you want to make a connection across the internet to the far end, you say, oh, hey, dear socket, extend yourself across the internet. Make the phone call to this host, data.pr4e.org, and on that port 80. So that's making the phone call. This is like the phone number, and this is like the phone extension. So we haven't sent any data yet. We have simply rung the phone of a process, hopefully living on port 80. If it's there, great. This might blow up. This one here won't blow up, but this line here could blow up. If there's nothing sitting on that process, it would come back and say, oh, you tried to call, you got no answer. That's a legitimate thing to happen. Maybe you don't have a network connection, or maybe that service is down on that server, or the whole server's down. But so it's kind of amazing that we're sitting here in Python, and in 3 lines we have probably 500,000 engineers have built this thing called the internet, all these protocols and all this software, and we just made use of it in 3 lines of Python. And I guess this is one of the reasons that people absolutely love Python. Absolutely love Python. So now that we have a socket, we have to ask ourselves, what kind of data are we going to send, and then what kind of data are we going to expect to receive across that socket? So now we have a socket, we are going to talk about what we're going to do with it, right? So the socket basically functions at this level. Your application is saying, make me a socket, which is sort of this endpoint, and then the connect actually connects to an application on the far side. And there's a port involved, so that might be port 80. And this is the far host, and that could be www.py4e.org or data.py4e.org. Okay, and so the socket is solving this, and the question then is, what are we going to send and what are we going to expect to get back? And that's what we call the application protocol. So we know that these two have made a phone call. And it's no different than making the phone call and saying, you know, hello, right? And everyone knows that when the phone rings and you pick it up, you're supposed to say hello. And that's part of our protocol. So who talks first, right? So the dominant protocol that we use in this section is the HTTP protocol. The key is Hypertext Transfer Protocol. It's dominant. It's really easy to use. That's why I use it as an example. But realize that there are many others like mail and file transfer and remote login and all kinds of other protocols. Each is a different application protocol. They all use sort of sockets at their lower level. But then on top of that, they layer the rules of the road for retrieving hypertext web pages. And we have used these for all kinds of other things. So the protocol, like I said, is like who answers the phone first, what do they say, what happens if the person doesn't answer right, can you hear me now, those kinds of things. And it's a real simple thing, and all you really need to do is so that both sides can agree, you have to write a thing that's like the rules in the middle and say, okay, everybody, as long as we all do this, we'll be fine. It's as simple as picking on which side of the road the cars can drive on. It works fine no matter which side, but if each car randomly picked, it would be really kind of a mess. So if you look at the typical URL, and this is one of the things that the web innovators in 1980 really invented that was wonderful, and it seems second nature today, but in 1990 it was rather revolutionary in that these uniform resource locators included in themselves a protocol, the host to connect to, and the document to retrieve. So this is one of the clever ideas that the web came up with, because we used to have to pick a program like FTP or Telnet or whatever, SMTP, then we had to go to the right host, and then we had to talk to that host a certain way. So in HTTP, it's a really simple protocol invented in 1989 and 1990 by Tim Berners-Lee and Robert Cailliau at CERN. And they created a protocol that we have grown to know and love and use for way more than retrieving documents, as we'll see in the upcoming chapters. So we're going to talk a little bit about what happens when you click on a page that has a link. Now, there's all kind of fancy stuff that can go on, but this is the basics. And so let's just imagine for the moment you are sitting looking at a web page, drchuck.com/page1, and inside that there is a hyperlink. It is a indication that says when you clicked on this page, go to a different page. And in that you see the name of the page that you're supposed to go to. So we click on this link, and that is a browser. This is an application, this is a process or an app that's running on your computer. This is the browser, okay? And when the browser sees the click inside your computer, then the browser makes a connection to port 80 on the web server, drchuck.com, and sends the request. This request that it sends is precisely specified by a standard, which we will see in a second. Then the web server does some magic work. Oops, let's go back. Then the web server does some magic work in here, reads some files, runs some code, does whatever, constructs an answer to our phone call, and sends it back. And it sends, in this case, back a web page in the format of HTML, the Hypertext Markup Language, which is different than HTTP, which is the protocol that we're exchanging. HTML is the format of the document we're getting back. And in this has an anchor tag, href and the end of anchor tag, and some highlighted text. And now your browser gets this back and then renders it according to the rules of HTML and CSS and JavaScript, etc., parses it, and then makes a pretty web page. And this web page happens to have a link back to the first page, and if you click there, it will do this over and over and over again. And that is the request response cycle. And that's governed by a series of internet standards. These are standards that were built from the 60s, 70s, 80s, and 90s and continue to this day by a group called the Internet Engineering Task Force, or IETF. The documents they produce are called RFCs, which stands for Request for Comments. The word RFC is kind of like a sort of joke, as it were. They're trying to be kind of funny in that. Funny is not the right word. It's ironic in that they're trying to say, even some of the protocols of the internet that we've used for several decades, they're always interested in improvements, and that's what the RFC stands for, and they're all named RFC-whatever. And if we were going to cruise around, we could find some various RFCs, and this is RFC 2616. It might have been revised since then, but this is like a document, and this is what they look like. Hypertext Transfer Protocol version 1. And so you're reading this document, you're going to write a browser, and you want to talk to the application protocol that is HTTP. This is one of many documents that helps define what HTTP is. So if you look down and said, oh, here's what a request looks like. This is how I'm going to get a document from the server. And you keep reading and you keep reading, and it says you're supposed to have the request method with a space, with the request URI, the request method with a space, with a URI, with a space, the HTTP version, and the carriage return the line feed. That's what it's saying. And so it looks kind of like this, right? We say get the document followed by a space. There's got to be one space. You do two spaces, and it's going to be quite frustrating, okay? And so this is an example that you can run on a number of on Linux operating systems and Macintosh operating systems with no changes. If you install Telnet on your Windows box, you should be able to run something like this as well. So Telnet is a program that we used in the old days. It used to be how we logged into servers, but because it doesn't encrypt your data back and forth, we don't use it anymore. But it basically is a program that can open a socket to a host on a port. And I'm saying Telnet to this host on port 80. And at this point, I am connected, and whatever I type on my keyboard is going to be sent to that server. Now, if you're doing this, you probably want to cut and paste this really fast, because if you take too long, most web servers will be like, you're a human. I don't want to talk to humans, I want to talk to programs. So remember to type this fast enough, and then you have to hit enter twice. So you have to have a blank line here. Just type this exactly as it's shown, and then you will get back the server. If you do it right, the server, and the server is properly configured, the server will give you back some headers. And this is metadata about the document you're going to get. For example, it's saying it's got text/HTML, which means that the remaining stuff is going to be in HTML, hypertext markup language. It has a blank line, and then the actual document, and then the connection is closed. And so if you do this, you can set this up in a way that you can run this on your own computer and in effect hack through the back door a web server. Now, you can't hack the secure web servers, and mail servers used to be easy to hack, but they're harder to hack now because they challenge you for information. But part of the reason I'm so obsessed with the command line is this is how real hackers work, and they know how to talk some of these protocols more directly. And so we think of this beautiful, sophisticated application talking to some other thing, and it's all pretty, and we got wonderful clicky buttons and nice usability. But the reality is, like in the Matrix Reloaded here, the kinds of things that really talented hackers are doing use command lines, and they really know what's going on, and that's how they do it. They understand what's going on better than the developers of the computers that are trying to be resistant to the hacking. So I come from a long line of using the command line, and that's why I encourage you to use the command line in this course. So the next thing we're going to do is we're going to go up into the application layer, and instead of typing those commands by hand, we're going to actually send them from Python and write a very simple Python web browser. In this section, we're going to write a web browser using Python. So we've already got a socket. We know how to write a socket. In the previous section, we played with the protocol, and use Telnet to do it by hand, and now we're going to do it in Python. And what you're going to find is it's not that hard. So here we go. So the first 3 lines of this program, import socket, make the socket. Remember, the socket isn't really got the connection. So when you make the socket, again, we're going to make a stream-based socket, and it's suitable for going across the internet. The connection, it's like ring, phone call, connect to data.pr4e.org and port 80. And so that basically says extend the socket across and connect to a web server. And so there's got to be a piece of software running, and this will blow up if the software is not running. Okay? So then, now we've got a phone. We've made a phone call. Now, whether or not the remote side says hello or not is up to the application protocol. And in this case, the web servers say nothing, and they wait for you to talk first. So we're the web browser in this case, and so we're going to talk first. And we know what, because we read the documentation, we know that we're going to send get blah, 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 space, blah, 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 HT1, and then 2 new lines. Return, return. Remember, you had to have a blank line. We'll talk a little bit about this encode. It's preparing the data to go across the internet. And then we say send it. And so this basically takes that little string and sends it across the network. And then this piece of software is waiting for it. And then the software goes and reads a file or does some other stuff, and then it starts sending us data back, which we can then choose to receive. So now I write a real simple loop. We're going to receive these things 512 characters at a time. So we're going to loop through, receiving 512 each time. And if we get 0 characters, that means it's end of the stream. The stream is closed. And if you look at the little example from the previous one, you saw connection closed. When the connection is closed, we get an indication that it is because we ask for some data and we get 0 data. Otherwise, if there might be more data, this will wait. If the network is slow, you'll see, if you do a print statement in here, you will see that this will pause from time to time on a really slow network. If your network is fast, it'll just go blank and it'll be so fast it won't matter. But this is how we go. So this is basically until the entire socket, until the socket is closed, we're going to read this data. And because this data is coming from the outside world, we have to decode it before we print it. And then when we're all done, we break out of here and we close the socket. So literally, that is an entire web browser written in 10 lines of Python. And again, this is why everybody loves Python. So this is what this program will show if you run. The get is sent. It looks exactly like doing it by hand. You get some headers. Again, this is metadata that tells you something about the file. In this case, one of the important things is what kind of thing is coming next. There's always a blank line as a break between the headers and the actual data, the metadata and the data. And then here is the actual text of that romeo.txt file. And then it's going to run this, going to print data.decode. All this is coming from the print statement. If you were going to parse this, you have to know that you're going to read the headers up to a blank line. The blank line is your indication as a software developer that the headers have stopped and the actual text begins, and you know the syntax. This actually could be a JPEG or a PNG or some kind of image, right? And this data would here look like blah. So if you type this and you change that code to actually go retrieve a JPEG URL, gibberish will come out, okay? And so that's exactly what you will see. And so now you have built a very simple web browser. Next, I want to talk a little bit about what happens when characters transition from outside your computer, from inside the computer in strings, out across these sockets to servers and then back. Hello everybody, and welcome to some worked sample code. If you are interested in the source code, you go to materials and download this sample code.zip. I have this downloaded. It'll be in a folder called code 3 on my computer. This is where I'm at. I'm in the code 3 folder, and this has a ton of bits of code here. So if I do an ls, you'll see I got all these files here, and so we'll just leave those there. And so this is the one I want to work through right now, is this socket1.py code. And basically what we're doing here is we're simulating what is going to happen in a web browser. And the cool thing about the HTML, the HTTP protocol, is that we can do this by hand. And I'm actually going to hack this HTTP protocol this is going to go to data.pr4e.org and retrieve a document. And so I'm going to do telnet to, now you can do this on a Mac and Linux, and if you put telnet on a Windows box, you can do it here, data.pr4e.org. And I want to talk to port 80, and the port 80 is a different port. It's a non-standard port, but what we're doing here is talking to the HTTP port. And so I'm going to be able to hand send commands to the web server and retrieve a document. So I'm going to cut, I've already copied this string, this get http romeo.txt. I'm copying that into my buffer because if I wait too long, this won't work. So here I go, and now I'm going to type that, and I have to hit enter twice. And that literally was the HTTP protocol. What I typed there was the HTTP protocol, and the web server responds with some metadata about the document, how much data there is, the kind of data is there. A blank line separates the header information from the body of the document. If I was to go to this in a browser, right there, you would see, and if I turned on Developer Console and I went to the network, let's make this a little bit bigger, you would see that it retrieves this file romeo.txt, and it gets back that, it tells us, it shows us the headers, and it shows us the response. And so this is all the same way of doing the same thing, and that is how to do the HTTP protocol. Okay? But now we're going to do this in Python. And so here's the code we're going to write. So we're going to import the socket library, and we're going to make a socket. Now this doesn't actually make a connection. Think of a socket as a file handle that doesn't have any data associated with it yet. And then what we're going to do is we're going to reach out and connect that socket to a destination across the internet with the domain name of data.pr4e.org. And the second parameter in this tuple, this is a function call with a single tuple as a parameter. And so tuple sub 0 is data.pr4e.org, and tuple sub 1 is the 80, which says I want to talk to port 80. That could fail. It will make the connection, and if the port 80 is there, away it goes. And then we're going to actually send the HTTP command. So get, this is the HTTP rules, followed by an end of line, followed by a blank line. So you saw me do this. This was what I typed here, and then I had to type a blank line. Now if you want to go read the RFCs for how to do this, you can figure this out. So the only other thing that's kind of weird here is we have to add this dot in code. And that's because there are strings inside of Python that are in Unicode, and we have to send them out as what's called UTF-8. And encode converts from Unicode internally to UTF-8. So this command is a set of UTF-8 bytes that we're then going to send. It still has that same set of characters in it, and now we're going to send it. And that's after we've made the connection, we're going to send these two things, and then we're going to wait. And my sock is like a file handle at that point because it's been opened and we've sent data. The HTTP protocol told us what we had to send and the fact that we did have to send it. So now I have just a simple while loop, and I'm going to ask up to 512 characters and receive up to 512 characters and get that back. If I will know that this is the end of file if I got no data back. So if the length of the data, the byte array that I got back is less than 1, then I'm going to quit. Otherwise, I'm going to print the data, and I'm going to use this decode, which is kind of the opposite of this encode. What I'm getting is UTF-8 encoded data, most likely, and decode basically converts it to the internal format called Unicode that runs inside. And so this is going to run a bunch of times, pulling in the blocks, basically 512, up to 512 characters at a time, printing it out, and then when it's all said and done, we will close that connection. And so it's not too exciting. Python 3 socket 1.py, and you'll see that it's just going to, Python is now going to do what I did by hand. Now of course the interesting thing is these are all in strings, right? And so this way we could write code that does stuff with this, but all we're really trying to do in this particular situation is show how you open a socket, send a command, and then retrieve the data. Okay, so now it's time to teach you a bit of complexity about text processing. Up till now, we've kind of been ignoring the complexity of text processing. Everything that I have been doing, most of what I've been doing is in ASCII, the Latin character set, the character set that, you know, United States, Europe, lots of Western civilizations use this character set. And if you go back to the 1950s and 1960s, we were happy to have one computer, and we didn't care what the character set was as long as what you typed on the keyboard came out on the printer. The internal representation didn't matter. And as the 70s and 80s came along, certainly 70s, we needed some interoperability, and so they standardized on a character set. But they standardized on a character set, certainly in the West, that did not represent anything. And so if you look at this at this sheet, basically what it's telling you is for the various characters, there's some non-printing characters, white space, non-printing characters, and then here's some printing characters like the and key, the 0, and then the uppercase characters, and then the lowercase characters. And there's 128 of these possible values. And there are nothing even for Spanish or French in here. And it's also why, by the way, uppercase lower letters in Latin sort lower than lowercase letters, and we saw that in some of the string stuff. And what these do is it maps and says, okay, and a lowercase a maps to the integer number 97, which in base 16 is 61, and in octal it's 141. But in binary, it's 8-bit numbers, and so these are 8 bits, otherwise known as a byte. And they're very efficient. Like you know, when you buy a disk drive, it's megabytes or gigabytes or whatever. That's how many of these kind of characters it can store. But unfortunately, this doesn't work for more complex characters. You can figure out these numbers inside of Python by using the ord function. And so you say, what is the ordinal, or the numeric representation of the uppercase h, lowercase e, and new line is a character as well. And so like 10 is the ordinal position of new line. And this actually has to do with sorting, so that lowercase e is higher than uppercase h. And that's just because in the simplest of sorts, we just sort them numerically. So new line, if you go back to the previous little sheet, new line is this 10 right here. It's that 10, which is a line feed, and that's a 10. And that's why when we print new line out, we get a 10. And so again, in the early days when strings were simple, we just represented them as 1 byte per character. But the problem is that, you know, as we have gotten more complex, and in today's modern world, it's simply unacceptable to say that the only thing computers can understand is ASCII. And so this leads to a from the simplest of character sets to a super complex character set called Unicode, which basically is billions of characters, potential billions of characters for every language and every character set. And because there's so much space in Unicode, it's easy to take very small variations of characters and give them a space. It's so large that you can have you can have pretty much any character that you want. So that's Unicode. The problem is that if we sent Unicode across the network, it would be way too large. It'd be this UTF-32, which instead of being 8 bytes per character would be 4 bytes per character. And so it would take all of the data that we build and make it 4 times larger. And it'd be very difficult. And so what they've come up with is ways to compress this. And UTF-16 is this weird thing. UTF-32 is really sort of the full Unicode, pretty much. UTF-16 is a subset of Unicode. It's used in some countries, but the best practice for moving data across the internet or in a file that you're going to move between computers is what's called UTF-8. And so what happens is that UTF-32 is fixed length. ASCII is one byte. UTF-16 is 2 bytes, UTF-32 is 4 bytes, and UTF-8 has dynamic length, meaning that it is 1 to 4 bytes, and if it's only 1 byte long, it's perfectly compatible with ASCII, meaning that an ASCII file is also a UTF-8. And so here's this little sheet. It's not critical that you understand this graph too much, but basically as time passed, 2000 internet's coming, now 2014, pretty much overwhelmingly the documents on the internet that you might retrieve are UTF-8. Now, so UTF-8 is the recommended practice, and it's sort of a compression of UTF-8 can represent all the things UTF-32 can represent. It's just a compression of it, so that, and with an overlap of ASCII, which is awesome. It's what you want. I don't need to talk anymore. So in Python, we have always had sort of two ways of representing strings. In Python 2, the normal string was a byte string, was an ASCII string, was a Latin string. And if you wanted to represent Unicode, there was a separate kind of object that we had. And so you would do that. And in Python 3.0 or later, one of the main features of Python 3 was to make Unicode and string the same. So that means inside of Python, when you have a string variable, it's a Unicode. Whereas inside of Python 2, it was a byte variable. And so now we have this notion separately in Python 2 and on Python 3 where we have byte variables. And so byte variables are, in effect, an array of bytes. So if there's ABC, that means it's 3 bytes. It's 3 bytes long. Whereas a string might be a 3-character string might be anywhere from 3 to 12 bytes long. So Python 2 had bytes and strings that were the same. Bytes and strings are the same, and Unicode is weird. And in Python 3, strings and Unicode are the same, and bytes are weird. Okay, and so that's what we've got to deal with. And there'll be times when we get bytes from APIs. When we call things, we have to then figure out what kind of thing those bytes contain, because the bytes might contain ASCII, they might contain UTF-8, they might contain various things. And so internally, all the strings in Python 3 are Unicode. Most of the time, if you're inside the program or reading and writing files, we just work. And that's why we haven't mentioned it. But now that we're talking over sockets, and we're talking to the sort of random world out there, we have to be a little more aware of the data we're dealing with. Now, the good news is 98% of the time, or 95% of the time, it's UTF-8, which might also include ASCII, and so it's quite nice. But we have to be aware of this. And so if we are going to take data that comes off of the network in the bytes, then we have to make sure that we interpret it or decode it and in the right way, so that internally the strings, which are Unicode, are properly represented. And so that's why when we read data in from a network connection like a socket, we have to say, hey, decode it. Now there's a couple things going on at that moment of decode. And so this is where we're doing it. We see this, we have to manage this in this code where before we send this stuff, we're going to encode it, which takes a Unicode string and turns it into UTF-8 bytes. There's actually a parameter here that you could do it different than UTF-8, but no one ever does. You might have to for certain situations, but so that says that we're going to encode this into UTF-8 before we send it, and then when we get something back, before we print it, we're going to decode it. And that's how this ends up working out. And if you look at the documentation, you will see that sometimes it says it's a string or it's bytes. And so you take a byte array and you decode it to get a string, and you take a string and encode it to get a byte array. And so that's what we're doing. So you can think of the process as this way, and that is the network has these UTF-8, mostly UTF-8 resources, not ASCII. If it's ASCII, it's okay. So you read with the receive. So this receive here pulls data, or well, we have a Unicode string. Let's start with the send. So up here we have a Unicode string. That's a Unicode string, even though there's no special characters in it, no Asian characters or French characters. That's a Unicode string, and before we can send it, we have to send it in UTF-8. If that had Asian characters, it'd be okay, and that would be set up just right so that the UTF-8 would be right. So we encode it first, and that's this CMD. This is now bytes. Okay, CMD is bytes, and then we actually send the bytes, and that goes across the network. We get back our thing, and we receive into data Well, data is bytes, not string. It's bytes. We can say how big it is. Function's kind of like a string, and it has len, except that it is 1 byte per character, which means some of it might be UTF-8. And then all we have to do is say decode. Again, you could, if you were dealing with a situation where you weren't expecting it to typically be UTF-8 or ASCII, you could tell it UTF-16 or something, and it's more complex. But the simple thing is you just say, I'm going to clean up my data on the way in. I'm going to clean it up by running it through decode.